So this is the second of the transition metal videos. This one's going to cover cobalt. It's like the little thing up there. Same sort of idea as the chromium video. It's going to go through the complexes, the substitution that sort of occurs, particularly looking at the complex ions, the formula of the ions, and also colours as well, which is something that people seem to struggle with. Cobalt's a bit of a trickier one. Chromium's a bit longer, a bit more to know. Chromium, there's just a bit more, the colours are a bit more sort of all over the place. There's a couple of sort of half equation-y bits which I'm going to run through, which are quite, potentially quite in depth, but have been asked in the past in questions, which as usual I'll go to at the end. Some exam questions which I found. I think I've got four different papers anyway, two from one. Go through, and there's quite nice calculation questions as well, which is actually incredibly hard. Conceptually quite hard, but anyway, I'll say that at the end. So, where to start? Beginning's a good shout. So, first thing is going to begin with this guy, which is the sort of the, I guess if you want the basic, the most sort of like, not easiest, but the starting place really, yeah, for cobalt, and that's this guy, which is the Hexa Aqua Cobalt 2+, and as it's written in this lovely pink colour, it's a pink solution. Obviously, colours being very, very important there. Solution just being my sort of abbreviation for solution. What I don't think I made very clear the last in the chromium video, and I want to make it really clear here, is this is just the metal ion complex. This is not the entire compound. This is just a single ion. Make that really, really clear. And I think I've neglected that in the past to sort of really make that point clear. But it's just the metal ion here, which obviously has the waters around it. In this case, this octahedral shape, and in this complex that it forms. So it's just the metal ion. I can't stress that enough. So cobalt 2 compounds potentially would contain this ion. So what reactions do we see? Well, I'll change back to a more normal colour now. When we use OH minus or NH3 ammonia, we're going to find that this guy, pinky over here, it's going to become, and I'll write all of this out, I'll be nice and correct, not including state symbols. It's fairly lazy of me, I think, really. But I just end up writing equations for hours, and I just don't really want that. So we react this ion, the cobalt Hexa Aqua ion. We're going to react it with, we'll do OH minus at the top, and NH3. That's a weird black, isn't it? It's like a grey. With this guy, and what we're going to produce is, and I'll try and get a nice colour. Yeah, we'll go with that. This little chap here, CO H2O4 OH2. Same thing again, CO H2O4 OH2, and then over here we're going to have 2H2O 2NH4+, which knows to balance this out as such. Colour here, and got quite a nice way of remembering sort of some of the states that I only just seem to have realised myself the other day, which is appalling really, I guess. If there's no charge, it's going to be a precipitate. I don't know how I've not realised that. It might be really clear to everyone else, really obvious, but somehow I've never sort of made that link. Anywhere where there's no charge, we've got precipitates occurring. So, cobalt ion here, obviously the OH minus, it's not a substitution reaction, it's stealing a couple of these protons, giving us the 4 H2Os and the 2 OH is left over. The charge is neutral here, has gone, because the 2+, obviously it cancels now, having the 2+ of the cobalt, the -1 from each one of the two hydroxides cancels it out. The H2O formed when the OH minus adds to the H+, to the protons there, the hydrogens. And a similar concept here, the NH3 is gaining a hydrogen ion each, forming the ammonium ion there. So, That's our first sort of little bit, and that's quite similar really to a lot of the other ones, Chromium and the other videos as well that will sort of show these bits, and they will have that sort of starting point of the, or I tend to start I think with the hydroxide, or certainly include it somewhere in there. I didn't start that at all in the last one, but there we go. So again, excess here. What happens if we had excess NH3? You don't need to know about excess hydroxide, in fact, on this one, I don't believe. No, you don't need to know about excess hydroxide, it's just excess ammonia. So, old Pinky, let's get back to here. There he is. We had excess, change the colour slightly, but still pink. So it's a pink solution, just in case. One of them. Keep to it. 2 plus. We react that with 6 NH3s now. Boom. And we are going to form, as you, oh no, don't want that. Undo, where's undo? Nope, that's just put another dot on. Oh, nailed it. I'm trying to think what colour, how I can do this one. No, that's green. That's a really horrible colour, but there we go. The colour here really is awful. And you can see here we've added the 6 NH3, so we're actually completely removing. This is a substitution now. Still the same charge, this 2 plus, and of course 6 H2Os which are left over as a result of sort of switching out the ammonias with the water molecules. This guy, and you can see this horrible colour here, it's charged again. It's a straw coloured solution. Straw coloured, sort of yellowy. What I've done is this sort of grimy, yellowy grime. 6H2O. So, and obviously here I will put the colour in. Pink solution there. So that's with excess ammonia. So that's our normal, not excess ammonia, forming as this intermediate sort of H2O for OH2, where we haven't, where we've got some protonation of the OH minus and the NH3 taking place. Then we've got full substitution occurring with the excess NH3. The next step is, I'm going into more detail here than I probably need to on this next bit, but I think it's worthwhile going into more detail than too little. Can't have too much of a good thing, I suppose, and cobalt is a good thing. The next bit is, I'm going to start with the oxidation. Oh, my computer's performance is slow. I don't believe that, that's a lie. Anyway, oxidation by air. So we're really looking at oxygen there within the air, giving us the oxidation. Now we're talking oxidation, actually, make this very, very clear. It's oxidation of this guy, so it's actually this that is being oxidized. Make that very, very clear. So we're going to start off with him. I'll stick with my colours. I'm not gonna cheat on it. So my CO complex again, NH3 6 2 plus, is ultimately, and this is the half equation just for the oxidation that's going to take place. It's ultimately going to be oxidized to, this is just, these colours are grim. How do you, where does that colour even? Yep, I've nailed that one. It's going to be oxidized, so the charge is going to increase, and that's all that's going to happen. So it's still the hexamine, hexammonia, hexamine. I forget now. Anyway, but now it's a 3 plus complex ion, and obviously half equations wise, to balance that up, we're going to put electron here, and also colour wise here, which I should state again, it's going to be a solution because it is charged. Dark brown solution occurring there. So that's what's happening to this guy here, which is the cobalt hexamine, I'm sure it's hexamine, being oxidized 2 plus to the 3 plus. But what's happening on the other end? What's the other part of the story? Well, the other half equation is involving the oxygen. And I'm just going to write out what the equation actually is, what the half equation actually is. You can get to it reasonably sort of easily. Oh no, I'll do it. It's kind of how it would be. So it's O2 ultimately, because oxidation is taking place here, O2 ultimately gets oxidized, reduced, sorry, to OH minus ions. When you end up balancing this up, you stick your waters here, and you end up having to balance it as such. Okay, spend your time going through that or learn it. It's doable. It's just a bit of a confusing one to sort of balance up, but that's basically what you get. And then it's the usual trick of adding these two together, which gives you, and I won't do the colours on this one, although that is straw, I'll just leave it as it is. No, I might change it slightly. Nice dark blue. When you end up just sorting this out, so you need to multiply this one by 4, we end up with 4, again this is for the oxidation with oxygen, or by air, 4CONH3, 6, 2 plus, add O2, add 2 H2O, becomes again the cobalt compound, 4 of him again, or her, it's not sexist, NH3, 6, 3 plus, and then our remainder, which is the 4 OH minus, loving life. Oxidation occurring there. Colours already given to you, it's fine. This is just the actual combination, it's the full redox equation, where we've got the reduction occurring of the oxygen to the OH minus there. Yeah, what I was thinking about so much therefore. Yeah, 0 minus 2, fine. So reduce, blah blah blah, oxidation taking place there. The other way we can oxidise, how much room have I got here? Have I got enough? Yes, dream. We can oxidise, and again it's of the same hexamine initial bit. I might be saying that completely wrong, I don't think I am. Oxidation using this time hydrogen peroxide. Same initial equation here. I'll write this out in just normal colours now. So it's the CONH3 6 2 plus complex going to CONH 3 6 3 plus electron, of course, both solutions, yada yada yada. And the other hand here, if you look at the chromium video, it's the same there, where our hydrogen peroxide H2O2 ultimately gets reduced down to the OH minus, stick in a couple of electrons, bish bash bosh. By the time you actually balance this up, multiply by 2 up here, full redox equation then is going to be 2 CONH. I'm taking just assuming here that at this point sort of redox and things aren't a problem. If they are, get it sorted. H2O2, well certainly the equations, and I mean equilibrium stuff's a little bit different. NH3 6 3 plus 2 OH minus. So 2 different oxidations taking place there. One via oxygen, one via if I can remember what it's called, that'd be great. Hydrogen peroxide, completely forgot there. Again, I think it's hydrogen peroxide actually. I think it's hydrogen peroxide in alkali. Yeah, hydrogen peroxide in alkali. So that's reasonably happy, hopefully. A couple of bits, and actually that's the theory side of this done. How much room have I got? Oh, I reckon I'll just get it done. Okay, so what's next? Well, classic with your carbonate ions. I'm doing with sodium carbonate, but as with the chromium video, I'm just going to cut the sodium out. It just ends up adding ions I don't really want. So I'm going to start with old pinky again. CO H2O 6 2 plus, again pink. I'll stick the colours back in now. Pink solution. I'm going to add to that the CO3 2 minus. Now because this doesn't have the acidic properties that the 3 plus ions do, looks terrible that. We get a different result, and really it's just a displacement that takes place. With the CO3 kind of jumps in, we end up with this compound formed. It doesn't really just, yeah, the water basically gets removed. We end up with this, which is, oh, I don't like that colour. CO3 plus 6H2O. And ultimately what we've got here is, again, no charge, pink still, but it's a pink precipitate. Key thing there. Not really much more to say about that, to be honest. That's it. That's it done. And with, I'm going to put conc HCl. I've got a feeling it needs to be concentrated, but I'm sure I've seen questions where it's not down as concentrated. Start with pinky again. CO. Oh no, stinker. What am I doing? COH2O 6 2 plus. This time it's the chloride ions that I'm reacting it with. So chlorides. And what I produce here is substitution goes on. Change my colour. And I end up with COCl4. Note the charge here of 2 minus. Each chloride giving us -1. Cobalt plus 2, so 2 minus in total. And obviously the displacement leaves 6H2O there, and we've got to balance this up, of course. One thing to make really clear here, well, first of all, is the colour. That's kind of a big one. Again, it's got a charge, so it's a solution. This is not cobalt chloride. Make that point. Right, so plenty of theory there. So we've started with, oh, off the page, like breaking the fourth wall. So cobalt there. Start with our pink solution. React it with this MOH minus and NH3. We're in this blue-green precipitate here, this intermediate if you like. Excess NH3 ends up in complete substitution. Straw-coloured solution there, which can be oxidised using oxygen or air, or it can be oxidised using hydrogen peroxide in alkali. That is an alkali. Remove the, again, moving the colours here, very similar colours. Same process, just a slightly different sort of overall equation going on. Sodium carbonate here with carbonate ions forming as a pink precipitate from the pink solution, and finally blue solution formed when we chloridise it. The chlorinate would be better, wouldn't it? Chlorinate the substitution going on to remove the waters. So we'll have a look at some exam questions now. As I said, 4 papers to look at. So it's question time. This one, question 7 from a paper. I don't remember which one now. Oh, Jan 10. It's a good year, great vintage. This question is about some reactions of cobalt compounds. One of these where you're given sort of a, I don't know what you'd call it, not a web. I want to call it a web. I'm going to go for a web, a flowchart, whatever it is. Starting here, we've got our cobalt chloride, pink solution, little aqueous guy here. We're adding sodium carbonate. We go to V, we go to Z, W, Y, and X from a variety of different sort of things being added. So the question is, give the formula of the complex responsible for the pink colour in aqueous cobalt chloride 2 and name its shape. So this is that idea that I said about in the sort of the theory half of this, is that whilst cobalt chloride may be the compound, the actual the complex that's given, as in this case obviously the pink colour, is that lovely, the hexa aqua 2 plus. Shape wise, again, it's just one of those sort of, we've got the 6 waters there, we've got the cobalt in the middle, and we've got the 1, I always draw this wrong, 2, 3, 4, 5, 6, so the octahedral shape, obviously similar to the AS sort of shapes, molecules and all the rest of it. So that's where we're starting here, and again, just to reiterate that point, it's not the full cobalt chloride that is giving it the pink colour, it's the cobalt complex ion, which can then bond with, in this case, the chloride ions, which is going to tie into another question which we'll look at in a few minutes. Give the formula of the cobalt containing compound V and describe its appearance. So we've got V over here, so we've got a reaction with the sodium carbonate. V is going to be COCO3. Again, just directly from our understanding, our theory of the cobalt chemistry. The appearance is going to be a pink precipitate. 2 more marks. Nice. Write an equation of the reaction that occurs when the pink solution is converted into W. So we've got cobalt chloride solution as a pink solution becoming a pale brown solution. What I would probably actually call straw. They're calling it pale brown. So the reaction that's going on there is start with our cobalt, which in this case obviously still the hex aqua 2+. Going to add our ammonia. I would always balance up at the end, although you can do it midway through if you want to. Still a complex here. We've got complete substitution taking place. There we've got the 6 put in, still a 2+, and in this case 6 waters are coming off. Balance it up with the 6 NH3s. That giving us obviously that pale brown, or what I would call straw-like colour. 2 more marks. So 2 marks are going to be for your general sort of ions, I'd guess, and then you're balancing on top of that. Keep going down. Okay, so cobalt containing compound in complex in X instead of the role of the hydrogen peroxide in this reaction. So, oh, gone far too far. So give the formula of this guy here. Right, so what's happened is we've gone from pale brown solution, we added hydrogen peroxide, and we've become dark brown. Oh, that just keeps going. X, so formula for that is going to be, it's still the hexaamine, but here it's been oxidized to the 3+, and so the role of hydrogen peroxide is an oxidizing. Oh no, not I don't know what happened there. Just froze. Oh, my computer is currently hating me. There we go, nailed it. Okay, so I'm going to leave that one there. Let's go on to the next one. I'm going to ignore this question down here. It's not, whilst it's about cobalt, it's not about cobalt and its colours and all the rest of it, so the theory is a bit different, so I'm going to leave that one for maybe another time. On to this one, which is from Jan 11, another January one. Hydrogen peroxide is used as an oxidizing agent in the preparation of transitional metal complexes. Consider the following reaction scheme. Start with our hexa aqua. We're reacting it to become the cobalt 2 complex, or whatever it is, and then we're becoming the cobalt NH3 Identify a reagent for reaction 1 and describe the colour change that occurs. Got a couple of options here. In fact, no, we haven't got a couple of options, have we, at all? Nearly got tripped out there. Yeah, ignore what I was about to say, I don't know what I was thinking. So we start with our cobalt H2O, so our hexa aqua, and we turn this cobalt 2 complex, which when oxidized becomes 3+. So to do this, we must add ammonia. So ammonia is added, that's our reagent. Describe the colour change. Well, we start with a pink solution, and we become straw coloured solution. What's funny is they say in the mark scheme it says allow pale brown, yet that is the colour in the past question that they actually gave for this complex here. Absolutely ridiculous. They make their mind up. They really will. So we're not having to worry about writing that just yet. So identify a reagent and describe the colour change. So colour change from the colour to the next one. There's your 3 marks. State the colour of the final solution formed in reaction 2. Well, the oxidation turns it as the 3+ here. Turns it dark brown. Okay, let's have a look at this. If there's any more. Is there any more? Nope, we're on to chromium, so that's that one done. Quite a nice little short bit there on cobalt. Bish bash bosh, finished. Another sort of reaction scheme one here, or web. I prefer the web. Don't like spiders though. We're starting here, they're giving us that starting point, the hexa aqua, and we're reacting it to produce Z, Y, W, and X. But we know that Z is a compound, not a complex. So straight away, I know exactly what that's going to be, but that's fine. Oh, we need to just do all of them. Great, 12 marks. Good number of marks. Good number of marks. So, where should we start? Let's start with Z, because I know what the Z is going to be. So, the pink precipitate, the compound that's formed is the cobalt carbonate. What do I have to do? Oh, good. So I've got to identify a suitable reagent. This is reaction 4 here. So that is Z. Reagent equals, don't, in this case, the sodium carbonate, don't put carbonate ions. That's not a reagent. That's the ion that's reacting. You've got to give it the full compound. So in this case, I've got sodium carbonate. I guess something like potassium carbonate would work, a named carbonate. Each of the reactions are write an equation for each of the reactions. Now the equation I would probably write as, yeah, we'll go write the full one out. Then I would suggest that you do use it as an ion in the equation because it just makes it a little bit easier. We're going to worry about the sodium then. We form the CO3 and 6 H2O. Oh, this is from June 12, by the way, this paper. We'll do this next one now. So we're going to a blue solution there. Blue solution, I think, is going to be the tetrachloride. So it's going to be, so this is reaction 3. So Y equals CO Cl4. Remember to get the charges correct. 2 minus reagent. I'm going to go concentrated hydrochloric acid, and then my actual reaction there, I'm going to put CO H2O6 2 plus add, it's going to be 4 Cl minus, isn't it? It goes to CO Cl4 2 minus, which works out fine, balance, and then 6 H2O. So that's Y. Might as well go to W next as our pale yellow solution. Again, pale yellow. Told you it's pale yellow. Straw colour, whatever you want to call it. Pale yellow straw. This one, let's go for ammonia. So reaction 1. What was it called? W. So it's been ammoniafied. So it's a CO. So reagent is going to be ammonia. Reaction, again, starting with that same one for this one. Last one, we're going to start with that. 2 plus, and that's going to add to that 6 NH3 to produce CO NH3 6, still 2 plus, and 6 H2O. And final one, remember it right, so it was the dark brown solution, so it's the oxidation one. So our X, it's going to be CO, same as before, but with the different charge. Reagent, I'll go for the hydrogen peroxide. The actual reaction then is going to be CO NH3, oh, it's a weird 3, it's a 3. It's a 3. 2 plus H2O2, CO NH3 6, 3 plus OH minus. I think we have to I believe that's balanced correctly. 4 plus, 6 plus, 2 minus, 4 plus. 2 of each of those, H2O2, yeah, that's fine. So, 12 marks there, good amount of marks. So there's our reaction 1, our Z, Y, W, and X. Are there any more questions I want to do here? No, I'm going to leave that one. Right, final question. This might be one of the hardest questions I think I've ever come across at A2. Well, A-level generally, I guess. It's not that it's necessarily difficult, but it's if you're not thinking about the sort of the right thing, it just all goes completely wrong. So basically, there's a lot of words So compound Z is a complex that contains only cobalt, nitrogen, hydrogen, and chlorine. A solid sample of Z was prepared by reaction of some cobalt chloride basically with ammonia and an oxidizing agent followed by hydrochloric acid. When this sample of Z was reacted with an excess of silver nitrate, 4.22 grams of silver chloride were obtained. Okay. Now I would think about, well, what's going to happen here? So we know we've got some aqueous cobalt 2 chloride. So straight away I'm going aqueous, so I know I've got this guy here. And I'm adding ammonia. Well, I'm adding ammonia. I'm going to get, oh god, CO, NH3, 6, 2 plus, 6, H2O. Then my oxidizing agent, so hydrogen peroxide, is going to essentially turn this into this. Key thing. Now we're told that we start with 50 centimeters cubed of 0.203 multiple centimeter cubed aqueous cobalt 2 chloride. So we can work out how many moles we've got of this. Okay, we can work out how many moles we've got of this cobalt 2 chloride. So not a problem. We know. I've lost the data again now. Where is it? So 50 centimeters cubed. So we want to work out how many moles we've got. Moles concentration times volume. So moles concentration times volume. I think it was 0.203 times 50 divided by 1,000. That was right, wasn't it? Yeah. And that's going to give us a value of. Let's get the magic calculator up. Boing. 0.01015. 0.0. Oh, that's quite clever. 0.1015. Is that definitely the value? Yeah. 0.01015. Good. So that's how many moles I added. Okay, which means when the whole sort of oxidation, all the rest goes across, that's how many moles I'm ultimately going to have left. I'm going to have that many moles of this. Because within my cobalt 2 chloride, I've worked out how many moles it contained of this complex. Working it through, it's ultimately going to be 1 to 1, that to that. And you might say, well, how do we know? Well, from the previous question, where we had the oxidation down at the bottom, yeah, it's 2 to 2, but that means it's 1 to 1. So basically, we know we've got a 1 to 1 reaction. The next part is to use the data given. So, which is obviously a fairly useful tip, I guess. Don't use other data. Don't use data that's not given. So we follow it by hydrochloric acid. And this is where the difficult bit comes. And what's happening is essentially that hydrochloric acid, you're going to form a compound now. So you're going to form, this compound, and essentially what's going on, that's this step here. So when this sample of Z, so Z being the compound that is formed in this whole bit, was reacted with an excess of silver nitrate, 4.22 grams of silver chloride were obtained. So if we say, well, we can work out again moles being mass over mR. We know the mass is 4.22. The mR of the silver chloride that's obtained is going to be a number. I know it's at 35.5. I can't remember what silver is. So silver's 107.9, which gives us 143.4. When we carry out our calculation, we get, let's calculify it, 4.22 divided by 143.4. Is that right? Yep. And we're going to get 0.029428. Just call it that. Yeah. So we've worked out the moles of cobalt complex that were added, which we can then equate to being the moles of cobalt in the final compound of Z through the oxidation and all the rest of it. When we add the hydrochloric acid, we essentially, because we're told that compound Z, so it's a Z, so we know that no sort of substitution is taking place. The chloride really here must have added to this compound to produce this Z, as I keep saying. We've worked out the moles essentially of chloride that were present in Z as well. And it says use this information to calculate the mole ratio of chloride ions to cobalt ions in Z. Well, we've literally just got to put 0.02942 to 0.01015, and we come out with a ratio of 2.9 to 1, and that's chloride to cobalt. So we've worked out our ratio. Okay, we've worked out our ratio, 2.9 to 1. Now, give the formula of the complex cobalt compound Z that you expect, that's the key word here, it's expect to be formed in the preparation described above. Now, taking it back slightly, so imagine this, just exclude the fact that it has the ammonia there. Let's just say it was cobalt 3+. Now we would imagine with a chloride ion that actually we would produce CoCl3. Now in reality, obviously when you add all the rest of the stuff in, it's going to be more like CONH36Cl3, but all we've really got is that just transposing down to there, but we're just giving it, sort of expanding it so it's the complex ion rather than just the simplified version. So we would expect to form CoCl3, but we can see the ratio is a bit dodgy. It's not quite 3, so the ratio here would be obviously 1 to 3. It's not quite in reality, and that leads us in the second. It suggests one reason why the mole ratio of chloride ions to cobalt ions that you have calculated is different from the expected value. So there's a few reasons that you could have. The first one could be that not all of the cobalt 2+, and we'll write it all out properly, was oxidized, or oxidation incomplete makes that a lot easier. That's one reason, which is valid. The other one could be some substitution took place. Probably a good sticker thing. So, e.g., we might have formed CONH3 5Cl2, for example. That's the kind of stuff we're looking at. Where in this case here, obviously these aren't free chloride ions, so aren't going to be picked up by the test for the silver nitrate. I'm not sure how much of a good job I've done of explaining that question, because I think it's a very, very difficult question. A lot to it, a lot of words. But basically, your compound Z, there's your preparation. We worked out the moles of cobalt ions that are in the original given volume and concentration, which transposes across to give us the the fully oxidized cobalt compound as a 1-to-1 ratio, which you can look at the equation and work that out. We can work out the moles of silver chloride, which is also the moles of chloride ions from the data given. We can then do a ratio easily. We can give a formula of the complex we would expect reasonably easy, and then suggest one reason. Well, there we go. Oxidation was incomplete. So there you go. I hope that's been of some help.